lab we're going to be doing is the Aspirator Lab, which is very dependent on flow rate and pressure. So I think it's important that you know a couple of features about the building you'll be doing it in.
So follow me to the service corridor.
This is where we keep everything that's ever broken in the engineering building, which is everything. We have garbage cans full of sand, we have wooden planks, we have that. I don't even know what this is. There's a really big scary saw blade and I kind of want to touch it, but I'm not going to. Got some broken computers here. I say just run a magnet over them and smash them up. I don't want them anymore. But most importantly over here, we have pump room, which is sealed tight. When you're doing your lab, you want the water flow coming out of the faucet to have a constant pressure and a constant flow rate. When you're at some place like your house, if you have too much water running at the same time, it affects the system. But here at Rowan Hall, we have a very big pump that kicks in and provides the pressure to the water that you need to get good results in your laboratory. When you're using the aspirator, you can't just do something like assume a perfect Bernoulli's relationship, because if you take a look at this cross-sectional cutout, there's changes in the diameter all throughout its structure. That's going to change your flow. Also in this cutout, there's some pieces missing, like a blue orifice where the faucet water initially goes in. You're going to need to be able to measure the diameter of this, and there's many different methods. One of it is to use a setup like this, piece of metal tape wrapped around it and push it into a point where it stops, and that's, you can just measure your tape thickness and that'll get you your diameter. Another thing to note is that in your D. Nevers textbook, the example given for a Bunsen burner aspirator is wrong. In this diagram, the flow is starting at the bottom and going through the top. This is all going in the positive Z direction. So in your setup of M1V1 minus M2V2, you keep it as M1V1 minus M2V2. But in the equation here, they essentially said M2V2 minus M1V1. The signs given for the velocities are incorrect. The way that an aspirator works is that the water flows through it vertically from the faucet. This creates an area of high pressure when it's going down this vertical direction, and this area has low pressure, and thus suction happens to make up the difference. Right now no water is flowing through the aspirator, so we're at 0 psi, but as soon as you start getting a flow, the pressure is going to go up. You can see you've got some suction from that. Unfortunately, you have to wait a while for the water to come out of the aspirator once you actually turn the faucet off. This has an application using the suction to move around fluid. Over here, we have the aspirator turned off and fluid on this tube. Because of that, the fluid level's at a constant height because nothing's happening to the system right now. Once you start putting flow through the aspirator and getting suction pressure though, there's going to start to be a difference in the water levels. Remember that pressure can be related to rho GH, so by measuring the difference between these two levels when you have a flow going, you then have the suction pressure for that flow rate. What you get when you're flowing water through the aspirator and you're also sucking water with the suction pressure is a modified flow rate, because not only do you have what's coming from the sink, you also have the water that you're sucking up coming out. This is the point of the second experiment of the lab, to see this relationship. So what you have are two graduated cylinders and a flow at a known flow rate. At the same time, you put this into the empty graduated cylinder, you put the suction tube into the filled one. So, in 3, 2, 1. Stop. What you have here is this graduated cylinder filled up with water and this one having some water taken out. And you have a time for that to happen. Meaning, you know the flow rate coming out of here, and you know the flow rate from the suction, which also lets you find the flow rate coming out of the faucet.